Find symmetric equations for the line of intersection of the planes. Our first plane is given by the linear equation 5x minus 2y minus 2z is equal to 1. And that means that a normal vector to that plane is given by what I'll call n1. Its components are the coefficients of x, y, and z, 5, negative 2, negative 2. Our second plane is given by the linear equation 4x plus y plus z is equal to 6. And so a normal vector to that plane, which I'll call n2, is 4, 1, 1. Again, the coefficients of x, y, and z. Let's see if we can understand what it is we're trying to find here. Let's suppose I got some plane existing in space, and then I've got another plane that is intersecting that first plane, and so it might look something like this. And you can see that if they intersect, it's going to be in a line right here. And we're trying to find the equation of this line. Well, we need two things to find the equation of a line in R3. One thing is a direction vector, a vector that tells me the direction of that line. I'll call that vector v. The other thing I need is a point on that line. We'll say that's this orange point right here. And so let's take one of these at a time. Let's start by finding the direction vector. We're going to use the normal vectors we found to find that direction vector v. Our normal vector n1 is going to look something like this. We could put it there if we want, and n2 may look something like this. Since our line lies in both planes, our line lies in the blue plane and the green plane, that means that line is orthogonal to both normal vectors, n1 and n2. And so a direction vector for the line can be found by taking the cross product of n1 and n2. That'll give me a vector which is orthogonal to both of those normal vectors and thus lies in both of those planes. So let's go ahead and find that direction vector v by taking the cross product of n1 and n2. And we'll do it by taking the determinant of this 3 by 3 matrix that has I, j, and k across the top row, 5, negative 2 across the second row, and 4, 1, 1 across the third row. And so this is equal to I times the determinant of the lower right 2 by 2, so the main diagonal, that's a negative 2, minus the off diagonal, which is a negative 2, minus j times the determinant of the 2 by 2 matrix we get when we block out the column and row of j rather. So the main diagonal is 5 times 1, or 5, minus the off diagonal, which is 4 times negative 2, which is a negative 8, plus k times the 2 by 2 in the lower right, the determinant of that 2 by 2. That's 5 times 1, or 5. Again, minus 4 times a negative 2 is minus a negative 8. So we have negative 2 plus 2, which is a 0 times I. And let's see, 5 plus 8 is a 13 times a negative j, so minus 13j. And 5 plus 8 is 13k, so plus 13k. And so a vector v that is a direction vector for this line is 0, negative 13, 13. Now that's a nice vector, but we can make it a little bit nicer. Let's go ahead and take our direction vector. I'm going to call it v in somewhat of an abusive notation. Take v to be, I'll just divide this entire thing by 1, or by 13 rather, to be 0, negative 1, 1. So of course it's still going to be in the same direction. We just divided it by a positive number. It's just a lot shorter vector. So it's still a direction vector, still tells us the direction of our line. Okay, next thing we want to do is find a point on our line. And so to do that, what we're going to do is find out where our line intersects maybe the xy plane or the yz plane or the xz plane. And so again, if it's on this line, it has to satisfy both equations of the planes. And so what I'm going to do is I'm going to take one of my variables to be 0. Let's go ahead and let z be 0. And then we're going to try and solve the resulting two equations and two unknowns in the variables x and y. So I'd have that 5x minus 2y is equal to 1, and 4x plus y is equal to 6. And again, what I'm really doing here is finding where this line of intersection of these planes intersects the xy plane. So let's solve this system. Easiest way to do it probably is to multiply the second equation by 2 and eliminate the variable y. It's going to give me 5x plus 2 times 4 is 8x. That's 13x. 0 y's there, because a negative 2y plus a 2y would be 0. 1 plus 2 times 6 is 12. 1 plus 12 is 13. And so 13x equals 13. That means x is equal to 1. And if x is equal to 1, then y would have to be equal to, let's see, 4x plus y would have to be 6. 4 times 1 plus y would be 6. Y would have to be equal to 2. So a point on my line is the point 1 for x, 2 for y, and 0 for z. And again, what we did is let one of our variables be 0, in this case z, and solve the resulting system of equations, 2 equations and 2 unknowns. So there's that point on my line, and again, let's label that. That's the point 1, 2, 0. Now we're ready to find the symmetric equation. I'm going to do it by first finding parametric equations. Let's pick some point that's on our line x, y, z. Form a vector from the point we know is on our line to that point we want to be on our line. And then if we take that vector, which is x minus 1, y minus 2, z minus 0, or just z, that has to be parallel to a direction vector, which I'll use this second v, 0, negative 1, 1. This will give us our parametric equations. X minus 1 is equal to t times 0, or just 0. Y minus 2 is equal to negative t, and z is equal to t. Solving each of these for t then gives me my symmetric equation. Yeah, because t is going to be equal to the negative of y minus 2, or y minus 2 over negative 1, and that's also going to be equal to z. So that is my symmetric equation, just 1 in this case, because it just relates y and z, but we should add in here that x is going to be constantly equal to 1. So let's add that into our solution. And then we have the symmetric equations for the line of intersection of these planes. Y minus 2 over negative 1 is equal to z, or z over 1 if you like. X has to be constantly 1.